Welcome to Chemistry 112. As you see, I'm rocking my Valentine's Day hoodie, staying warm, managed to walk to class, but then again, I don't live that far away. So hopefully you guys are staying warm, staying safe. I have no clue what we're going to do about lab just yet. We'll figure things out as we go. But for right now, prepare for the lab. We'll probably end up doing lab number 3 at some point, because it is a interesting lab, to say the least, to actually see this is how you would go about taking the data to get all this kinetic stuff. But if we push it back a week, I'm sure that's going to greatly help the Monday, Wednesday, Friday class, which is pretty far behind. So let's go ahead and start by going to the PowerPoint. I'll have to spend a minute once I plug in the doc cam, so we're almost done with chapter 15. When we finish chapter 15, then we're going to start to review, and then sorry. Once we review, we can start thinking about test number 2. So, but that's still a little ways away. We have a couple more concepts. This might take us the whole time. If not, I'll go to some achieve homework. Hopefully, though, pardon me. Hopefully you're using the snow day to get at least a little bit of the homework, look at a little bit of the homework. But okay, so previously we talked about the equilibrium constant K. K was, if you remember, the ratio of products over reactants, either in gas phase or aqueous phase. No solids, no liquids, but it's the idea that at equilibrium, the forward reaction is at the same speed of the reverse reaction, so it's essentially like on a treadmill, the reaction seems to be stopped. Now, given an infinite amount of time, all reactions will reach K. But how can you find out if a reaction is at equilibrium when you don't have that time to wait around? And this brings up the concept of reaction quotient Q. So we're going to take essentially a snapshot of the reaction, looking at the reaction progress. If you know what K is supposed to be, and there's many ways to determine K, we won't get them right here in this chapter, but there is ways to determine K. But there's a lot of equilibrium constants that are very, very well known. In fact, the whole acid-base chapter will all be about equilibrium constants of acids and bases. And when we get to solubility, solubility is a reversible reaction with a very well-known equilibrium constant. So there's many, many equilibrium constants that we know that we're not going to touch in this chapter. But if K is specifically defined the ratio of products to reactants at equilibrium, we can define Q as the ratio of products to reactants at any point in the reaction. So it's essentially the same thing, except K is very narrowly defined. It's very narrowly defined as only at equilibrium. Q could be at the initial point of the reaction, could be at the ending point of the reaction, could be where we have all products and no reactants, could be where we're a 1-to-1 ratio of products to reactants. It doesn't matter. Q is just the reaction quotient at any time in the reaction. Q can be at equilibrium, but it doesn't have to be. So we're going to set up Q the very same way we set up K. And based on comparing our Q to a known K, we can determine where the reaction's at. And so what we reaction of I keep on coming back to this one because I like to use real numbers, and this one is known, and I bothered to look it up. K sub p of the Haber-Bosch process, the Haber process, where they made Germans figured out how to make ammonia for fertilizer very, very efficiently. Managed to get this to work. So the Kp of this is 0.105. So given these three situations, where is Q and which way would the reaction go? So remember, whatever Q is at, Q wants to shift to get to K. So you have to think about, what is this ratio? What is the ratio of ammonia to nitrogen to hydrogen? As one goes up, one side goes up, the other side must go down. So Q will always shift to K. If Q is too big, it needs to go down. So how do you get a fraction to go down? You increase the denominator while decreasing the numerator. If it's too small, you do the opposite. Increase the numerator while decreasing the denominator. So let's go back to the slide real quick, just so we can write down these numbers. So our Q sub P is the ammonia squared over nitrogen to the first, hydrogen cubed. All that, remember, is from our coefficients. This is unlike kinetics, and where the coefficients absolutely matter. We got situation one where, let's see, hydrogen, nitrogen, ammonia. We have 4, 3, 1. Situation two, we have 2, 1.5, 1.75. We have 3, 1, 1.68. So let's look at this. And remember, our K is 0.105. Okay. From here, go to .cam. Okay. So we're just plugging our numbers in. If I have 1 squared over 3 times 4 cubed. So make sure we do it right. 1 over 3 over 4 root 4 power 3. So Q is equal to 0.00521. Now, how does that compare to K sub P? Q is less than K. So what does that mean? Q is less than K. We need to increase the Q, which means we need to increase this number while decreasing these two numbers. So as this number goes up and these numbers go down, this ratio will increase. Let's look at situation two. So 1.75 squared over 2 cubed times 1.5. 1.75 squared divided by 1.5 divided by 2 root 3. I don't know how we managed it, but we got an overabundance of products. So in this case, Q is greater than K. We've shot past equilibrium. So what's going to happen at this point is the ammonia will start to break down and reform our nitrogen and hydrogen. Somehow we pushed it too far to the right, and now it's going to shift back to the left. So this number is going to break down, get smaller, and these numbers are going to increase and get bigger. So the reaction will have shifted left. The reaction will have shifted right. Now, in the last situation, 1.68 squared over 3 cubed times 1. 0.68 squared divided by 3 root 3 divided by 1. It gives you 0.10. Well, this is going to round up to 105, which is equal to our K sub P. So at this situation, we would be at equilibrium. Q equals K. We're at equilibrium. So under these situations, the reaction would seemingly stop. The amount of nitrogen would stop being consumed. The amount of hydrogen will stop being consumed. The amount of ammonia will stop being formed. The reaction essentially ceases. So by looking at the difference between Q and K, we can decide which way the reaction will shift. Now, the hardest part of this chapter will be what's called the ice table. Sometimes we do not have all the equilibrium concentrations, and we don't have our K. So, in fact, we're going to have a lab like this at some point where we don't always know all of the concentrations. At most, we can only know maybe 1 or 2 of them. But if you know how you set it up, if you know where you started from, you can still calculate equilibrium given K. So assuming you're not just handed a random vial, assuming you mix 2 chemicals together and let them react, and then you measured one of the products or one of the reactants, you can know everything about that equilibrium situation. Now, this requires a little bit of pre-calculus, something called the ICE table or ICE table. It stands for initial change in equilibrium. We can solve for our K. Now, the example that we will do in lab, and the example that is given because it's so very easy. So we mix iron, which is vaguely yellow, rusty, with thiocyanate, which is colorless. When they mix together, they form an iron thiocyanate complex that is like blood red. And the deepness of the red is dependent on how much iron and thiocyanate we have. The reaction can be simply described as thus. But because of the deep red color, we can easily measure the wavelength of absorbance. So if this appears deep red, this absorbs strongly in the green wavelength. And we can measure this and figure out concentration of iron thiocyanate based on the Beer's law, based on absorbance is equal to the molar absorptivity times path length times concentration. If we know the molar absorptivity, we can directly find the concentration. So what we're going to start out with 3 facts. Our initial concentration of iron, our initial concentration of thiocyanate, and what we're going to have our measured concentration of iron thiocyanate at equilibrium. Because we know we are mixing these in situ or mixing them as we do the reaction, the amount of iron thiocyanate currently in solution at 0.0 at the time of 0 is 0. Before we mix them, the concentration of iron thiocyanate is 0. Once we mix them at equilibrium, the concentration is the one you can see. So what we're doing, so how we're setting this up, ICE 0.0005 0 0 0 3 zeros and a 3 0 iron thiocyanate and iron thiocyanate. 4 zeros and a 5. Now, it's already worked out here, but let's look at this. This is what you would be given. This is what you'd be given on a problem. We can say, if this is our initial concentration of these two reactants, what is K if iron thiocyanate is this molarity at equilibrium? So they'll have words like initially, which will tell us these concentrations, and concentration at equilibrium. So whether it's a reactant or a product, it doesn't matter. And from there, we have to fill in our table. So the idea here, where the pre-calculus comes in is, in order to get from 0 to some concentration, we have to go up by a factor of x. Now this x is going to be times whatever coefficient we have here. So since there's no coefficient, it's 1x. So this goes up by a factor of 1x. We don't know x, but based on this, we can figure this out. Now, because this is going up by 1x, these guys must go down by 1x and 1x. Equilibrium is just the sum of the initial and the change. So at equilibrium, the concentration of thiocyanate is 0 plus x, which is just x. So right now we know our x. Now for thiocyanate, it would be 0.0003 minus x. But since we know x from here, we can figure this out. 0, 0, 0, 3 zeros and a 3 minus 0.0000546. 0.000245. And this one would be 0.0005 minus x. So this would be 0.00044454. Yes, I just did that math in my head, but it's... Now we have equilibrium concentrations for all things involved. So we can set up our K. K is equal to 0.000, 4 zeros and a 5, 4, 6 divided by 3 zeros, 4, 4, 5, 4 times 3 zeros, 2, 4, 5, 4. And so we can solve our K. Yes, this might have been easier to leave in scientific notation, but we're going to go ahead and keep it like this for now. 0.0002454. So we get our K, in this case, is 499.5, which is, we're going to go ahead and round up to 500 with a period after it to signify 3 sig figs. So we found our K for this reaction. And that's what we would have found here. So we found our X. We plugged our X in for here and plugged in our values. You're going to get used to setting this up. So looking at our ammonia reaction. So write our equation down. 3H2 plus N2. Hopefully this is old hat at this point. 2NH3. Our K is, well, actually, I'll write our ICE right there. ICE. I'd say if the initial pressure is 3 atmospheres of hydrogen and 1 atmosphere of nitrogen before we mix any ammonia. And at equilibrium, the equilibrium pressure of ammonia is 0.706. what is our K? K is going to be ammonia squared over hydrogen cubed times nitrogen. What is K sub P? I've set that up. So this is what you would be given from the get-go. So note here, so when this reacts, you would produce two equivalents of X. When this reacts, we would lose one equivalent of X. And when this reacts, we would lose three equivalents of X. So this is going to be 3 minus 3X. This is going to be 1 minus X. And this is just going to be equal to 2X. So if 0.706 is equal to 2X, what is our X? 706 divided by 2 is X is 0.353. So 1 minus 0.353 is 0.647. And 3 minus 3 times 353 is going to be 1.941. Now it's just a matter of plugging everything in. 706 squared divided by 1.941 cubed divided by 0.647 to the first power. 706 squared 1.941 root 3 divided by 0.647. I mean, we already know what the K is because we've done this one a couple times, 0.105. But if you didn't know, we found it mathematically through the ICE table. As I said, the ICE table is the hardest thing you'll have to do with this chapter because it takes a little bit of reasoning. It's not something you can just punch through. Oh, got a lag. Give me a second. Okay, there we go. Okay. Set that up, solve that. 105. We'll do some of the problems. We'll do some of the problems in the achieve in a little bit. Now, you can also use the ICE table when K is known. We can solve for this, but this is what we'll have to do when we get to acids and bases next chapter. We will not be really doing this part of it on the homework or on the test. But I just want to give you a preview of what we're going to see. On a situation, 0.25 molar solution of hydrofluoric acid has an equilibrium constant of 7.2 times 10 to the fourth. So the reaction HF breaks down reversibly to H plus and F minus. At I, we know the concentration is 0.25, and the H plus and F minus is essentially 0. And we say, okay, we don't know any of the E concentrations, but we do know K sub A. 7.2 times 10 to the negative fourth. So let's show how I got that. Let's go through it systematically. Now, because K is not 0, if K was 0, then these numbers as 0 can hold. But if K is greater than 0, most times it is, there must be some concentration because 0 divided by any number is itself 0. So that means for the reaction to proceed, you have to have some increase of H plus and F minus. And that means you'll have to have some decrease of HF because Ka is not 0. Setting this up at equilibrium, this is 0.25 minus x. And these are just x and x. Now, setting that equal to K. The Ka equals H plus times F minus over 0.25 minus x. Sorry, all over HF. Sorry, I plugged in things too early. Now, plugging these in, we have 7.2 times 10 to the negative fourth equals x squared, x times x, over 0.25 minus x. Now, from here, what we got to do is we got to do a little something called a quadratic, as we'll see in the next slide. Now, there's ways to make this there's ways to simplify this, but this might not be the case. Now, quadratic, remember, is a parabolic function given as the equation ax squared plus bx plus c, where there's two possible solutions where this crosses the essentially the x-axis. What is it? Yeah, two possible solutions that crosses the x-axis, where this equals 0, or y equals 0. Now, always one of these values will be real, one of these values will be false, because we're dealing with real numbers. In math, both numbers would be valid. But however, we're dealing with real concentrations. There's always going to be a possibility that's either going to be negative. Can you have a negative concentration? The answer should be no. Or the concentration is going to be too large, meaning you're going to have more material than what you started with. Since I started with 0.25 molar, there is no way to get more than 0.25 molar worth of H plus or F minus. If I get 0.35 molar or 0.4 molar, I know that's no longer a valid solution. But our quadratic equation is negative b plus or minus the square root of b squared minus 4ac all over 2a. So the trick is to get that into that function. So let's show how we can go about doing that. So from here, here's where if you have to do the quadratic, well, I would say I pity your soul, but I'm going to try to avoid it for the most part. It's not going to be something I throw that often, but it will come into effect probably at least on the homework once or twice. I'm not sure whether to do that on the test for test 3. But okay, so we need to get this out of a fraction and into the thing. So we're going to cross multiply both sides by 0.25x. 25 minus x. So you're going to have 7.2 times 10 to the negative fourth multiplied by 0.25 minus x. All that equals x squared. From there, we need to evaluate within the parentheses. So it means you got to multiply 7.2 times 10 to the negative fourth by 0.25 and by negative x. So 7.2 times 10 root negative 4 times 0.25 is, so we have 0.00018, and we have negative 7.2 times 10 to the negative fourth x. The last step to get this into quadratic formulation is to get all these to one side. It's better to have a positive x squared than have a negative x squared. So I'm going to move that to this side and that to this side. So I'm going to add 7.2 to both sides. So we have 0 equals x squared positive 7.2 times 10 to the negative fourth x and negative 0.00018. So in this case, our A is 1. Our B is 7.2 E negative 4. And our C is negative 1.8 E negative 4. So looking at our quadratic, which is negative B plus or minus square root of B squared minus 4AC all over 2A. We have negative 7.2 E negative 4 plus or minus square root of 7.2 E negative 4 squared. I'm going to go at negative times negative makes this positive, so negative 1.8 E negative 4 times 4 all over 2. So let's evaluate everything within that square root. 7.2 times 10 root negative 4. I'm going to square that. Then I'm going to add 1.8 times 10 root 4 times 4. And then, oh, geez, I screwed that up. So add our 1.8 times 10 root negative 4 times 4. And then we're going to square root that. So we square root all that, and we have that whole thing. I'm going to flip pages real quick. So we have negative 7.2 E negative 4 plus or minus 0.02684, we'll say 25 all over 2. So take that minus 7.2 times 10 root negative 4 and then divide by 2. You get one answer is 0.013, we'll say 1. And doing the other value, so 7.2 times 10 root negative 4 would get the other answer is negative 0.0138. Now, looking at that, there's only two possibilities that make sense. There's only two possibilities, but only one of them makes sense. One of them has a positive concentration. The other has a negative concentration. So the only possibility with any validity is the positive one. So we found this is the concentration of acid and the concentration of F minus at equilibrium. And that's the hardest thing we can do. Now, as I said, there is some ways to simplify it so you don't have to use the quadratic, but they do not always work as accurately. I wanted to show you and work through at least one quadratic problem. So, one quadratic problem before we move on. Now, had you used the shortcut for the quadratic, what you would have gotten is 0.0134, which honestly is not that far off, but sometimes that little bit changes the things. Now, this is one that's kind of on the borderline of whether you can shortcut it or not. So you might, if you considered the fact that it is, I gave you two significant figures of concentration, you could probably shortcut it. So the concentration is actually 0.013, and that won't change. Okay, here's the shortcut method. Now, if the equilibrium constant is significantly smaller than the initial concentration, then it is possible to simplify this so you don't have to use the quadratic. Now, the hard fast rule is that if X is smaller than 5% of the initial concentration, X is not significant to this. And so how can we determine that? And the way is we look at the initial concentration divided by our K. If this number is greater than 400, then the concentration change will be less than 5%. So in our previous situation, 0.25 divided by our 7.2 times 10 to the negative fourth, I would have said that was 347, which is less than 400, so it's not insignificant. Not insignificant. If we do this instead with this carbonic acid with a smaller K value, we get, instead of 347, we get 1389, which is much, much greater. Much, much greater than 400. So what happens if the idea here is that if X is less than 5%, then that 0.25 minus X essentially becomes a rounding error. It essentially stays 0.25. It's instead of like if it was 5%, you would have had it went down to 0.24 something. I'll say like 248 maybe, or 2475. Now, if it's less than 5% and you get 0.2499, wouldn't you say that, oh, that rounds back up? That rounds back up to 25. And that's essentially what we're saying. That in the case of, well, this is greater than 400, we can make the assumption that that minus X is essentially not there. Now, these X's are still valid. These are still valid changes, because going from 0 to any number is a big change. But from going from 0.25 to 0.244243 is not much of a change that we would notice. And so we can actually abbreviate that, but okay. Now, the last concept of this chapter is the Chateliers. This is the one part of this chapter which is not math, which, yay, there's at least one part of this chapter that is not just dense number theory. So we're always going to go back to the Hopper process because that is one that is so very important and such an interesting story there. You looked at that. We said the Kp was 0.105. You looked at the concentrations. This one only goes to about 35% yield. Like a third of the product that could possibly be produced gets produced, which is not good. And it's not good at all. It's a very wasteful process right there based on that. So how can we make this economically viable so that we can fertilize all these crops and provide cheap ammonia to use instead of we have to have the farmers going out and putting the night soil out on the field? How can we use cheap fertilizer that could be readily produced? Well, we have a French chemist named Henri Louis Le Chatelier proposed this principle of how by disturbing equilibrium we can force nature to compensate. It wasn't until I think the Germans finally figured it out for the Haber process, but Le Chatelier's principle holds true regardless of who invented it. The idea that at equilibrium, Q equals K. So what are we going to do? We're going to change the situation so Q no longer equals K. So what does the reaction have to do? It has to shift to fix that, to reestablish my K. K does not change when I change concentrations. K is set at a given temperature. And so the system will always autocorrect back to Q equals K. Now, so K is constant for a given reaction at a given temperature and will not change if we change a concentration. So the idea here is what happens when I change a concentration? Q is our ratio of products to reactants. If we add only one thing, if I add to the bottom, what happens to Q? Well, if I increase the bottom, the denominator, Q would go down. When Q is less than K, what happens? It has to shift towards products to replace it, to increase back up to K. If I add a product, I add to the numerator, Q is greater than K. So what's got to happen? We're going to go from products back into reactants until Q equals K again. So think about it like this. If I add something to one side or the other, the reaction shifts towards the other side. If I add a reactant, Le Chatelier says the reaction shifts towards products. If I add a product, the reaction shifts towards reactants. It always shifts away from the change. Now, we can accomplish the same thing through a removal, but it's a reverse thing. If I remove a reactant, I am decreasing the numerator. If I decrease the numerator, I get Q decreases, and Q is if I remove a reactant, I decrease the denominator. The Q increases, and thus we have to shift towards reactants. If I remove a product, I decrease the numerator, Q goes down, so I have to shift towards product. So if I remove from the left, it has to replace to the left. If I remove from the right, it has to replace to the right. Essentially, the reaction will shift to undo the change you did. It's like a little robot coming behind and sweeping up after your mess. You come in and dump some trash over here. You have your Roomba come by and try to fix it, to clean the room up where it was before you came in and junked everything. So you add a reactant, reaction tries to remove it again. You remove a product, reaction tries to add it back again to get things back in balance. The most common way to remove a product would be to, say, turn it into a liquid, condense it. Because remember, liquids and solids did not play a part in the equilibrium expression. So if you turn it into a liquid and trap it as a liquid, suddenly it's out of the equation. Now there's two other ways to change this. One way is to change pressure and volume. This only works with gas phase molecules, but a change in pressure or volume will result in a change in their concentration. But this one is not so easy because you have to look at which side has less gas molecules and which side has more gas molecules. Because let's reason this out. So I'm going to go to the example of our Haber-Bosch because it's so easy and readily available. Okay. Go back to the document camera so we can look at this. Looking at this, how many gas molecules do we have on the left? We have 3, 4 gas molecules. In an ideal gas, it doesn't matter what we have. There's 4 gas molecules. On the right, we have 2 gas molecules. So think of it like this. If you start compressing things down, you increase the pressure, you decrease the volume, what's going to happen? We're going to try to release the pressure. How do you release the pressure? By decreasing the moles of gas. Because remember, Avogadro's law for gases is that volume is directly proportional to moles of gas. So if the volume decreases, we must also decrease the moles of gas. We are trying to fix that. If you increase the pressure, you're decreasing the moles of gas. So we're going to cram 4 molecules, cram them closer and closer and closer together until they're crammed into 2 molecules that take up less space. So by putting this under high pressure, you can force it to products. Inversely, if you put this under low pressure, these gas molecules have a chance to split apart and break back apart. So low pressure would shift it towards here. Going back to the original equation we looked at the very beginning, we said 2 NO2s can go to N2O4. High pressure pushes them together. Low pressure would shift it back because 2 is greater than 1. Even though this is a bigger molecule, 2 gas molecules still take up more room than 1 big gas molecule. Now, the other way is by changing the temperature. Now, this is the only time when K will change because K is dependent on temperature. It is a thermodynamic process. Now, how do we figure this out? We have to look at the thermodynamics of the system. You cannot know this without knowing delta H, whether the reaction is net endothermic or exothermic. When this is endothermic, our delta H is a positive value. For endothermic, heat goes into, and delta H is a negative value when it's exothermic. Heat is produced, heat is exiting. Now, the idea here, how does temperature change this? Technically, in an endothermic system, higher temperature means greater K. Lower temperature means lower K, and the vice versa for exothermic, but that's really hard to wrap our minds around. The easier way to look at this is whether heat is a product or reactant. Heat is a product or reactant. And when you change the temperature, you're essentially adding a product or reactant. And then we can see how the shift would occur. So let's look at this one. Let's say this is, let's say this is exothermic. This process produces heat. So we put heat as a product. It's like so you'd say negative 500 kilojoules or something like. So if I increase the temperature of the system, what's going to happen? Well, if I increase the temperature, I'm adding heat. And so I'm adding a net product. So what's going to happen if I add a product? Le Chatelier says I shift back towards reactants. Shift back towards reactants. If I'm decreasing heat, decreasing the temperature, I'm removing a product. If I remove a product, the reaction has to shift to replace that product. So if I remove temperature, I would shift it back to the products. In the case of exothermic, so in the case of endothermic, heat is a reactant. So pumping more heat would shift it towards the product side. Decreasing the heat would shift it towards the reactant side. And so that one's a case you have to look at it reaction to reaction, but you cannot know this one without first knowing the delta H. So you cannot answer that question without that. So let's look at the Haber-Bosch show, the Haber process. What would adding hydrogen do? Adding hydrogen, you're adding a reactant. You're going to shift towards products. What would removing ammonia do? Removing ammonia is going to shift towards products. A decrease in volume, which is an increase in pressure, 4 moles of gas to 2 moles of gas, going to increase products. Decrease in temperature, we're removing a product, shift towards products. So addition of a catalyst. What would a catalyst do? Now here's the trick question. What would a catalyst do? Nothing. A catalyst speeds up the reaction, but it speeds up both the forward and reverse reaction. Speeds up both the forward and reverse. Equilibrium is defined as the ratio of the forward and reverse rates. A catalyst never helps us produce more product. It just helps us produce product faster. Instead of a 1,000-year time scale, maybe it's 10-minute time scale. But it still just helps us reach equilibrium that hasn't changed. Catalyst does not help us get more products. But all these things are what they had to do to make this reaction viable. Pump in a ton of hydrogen, condensed ammonia, do this at a really high temperature, and they chill it. Well, the chilling effect helps condense the ammonia and helps get this whole process. There's a whole weird setup here that keep on pumping hydrogen, get high pressure but low temperature, which condenses the ammonia and further strives this towards products. But this was the way, essentially, we got a good, like, ammonia produced economically so that we can actually use that in fertilizers. Okay, that's the end of this chapter. So we have, let's see, a few minutes left. We can look at some of the homework, assuming we can get this up. So I just want to look at, okay. Yeah. So chapter 11 is our first ICE problem. And what's more, they don't actually give us concentration, but they give us moles and liters. Moles and liters. So it is very possible to calculate concentration. So let's write out our situation. 2SO3 goes to 2SO2 and oxygen. ICE. They give us this number, 0.680 moles, and this number, 0.150 moles, and they give us a volume of 2.50 liters. And they want us to find K. So with that in mind, the first step we must do is find what is our molarity. To do that, we're going to take our moles divided by our liters to get molarity. So 0.68 divided by 2.5 gives us the molarity of 0.272 molar. And our 0.15 divided by 2.5 gives us 0.0600 molar. Now, initially, if we put this into a container and let it break apart, at the initial point, that would be 0 and 0. So the change going from 0 to 0.06 must be positive x. The change here must be 2x. The change here must be negative 2x. Now, fortunately, we know our x. So double that would give us the amount of SO2, which would be 0.120 and 0.272 minus 2x would be 0.152. So I just took this number minus that number. Lastly, to find K, products over reactants. So 0.120 squared times 0.060 all over 0.152 squared. Products to their coefficients over reactants to the coefficients. So 0.120 squared times 0.06 divided by 0.152 squared. And I'm given a K of 0.037, we'll say 4. 374. So, looking at this, we're given the concentration of the products at equilibrium is this. What is the concentration of PCl5 at equilibrium? So this one is a nice problem that we know K for, but we don't know the PCl5. However, we don't need to know, this one's actually, they already give us the concentration at equilibrium. So we don't even need a ice table. Cl3 times Cl2 over PCl5. Set that up. That is equal to 0.0420 equals 0.13 times 0.12 over, we'll just say x. Or x. So now how do you get x by itself? You're going to get x to this side and this over here. So rearranging this, you get x is equal to 0.13 times 0.12 all over 0.0420. So we're just rearranging. This is why we wanted you to have some level of math before coming into here, because you need to be able to efficiently solve for this once we set it up. Now, hopefully this is not too bad. I try to throw these reasonable problems at you. 371 would be our concentration of reactant at equilibrium. 371. So, okay. If this one's a Q equals K, if Kc is 15, what will happen when I mix these three gases? SO2, 2SO2, O2 goes to 2SO3. We saw this equation, but in reverse. They give us concentrations. What you have to do is set up your Q, which is be SO3 squared over SO2 squared times O2, and find it. Your value. So 0.6 squared divided by 0.6 divided by 0.2 squared would give us 15. This first situation, Q equals K. So the reaction is at equilibrium. What about the next one? 0.4 squared divided by 0.1 divided by 0.15 squared. So I'm setting up products over reactants. I get 71. Q is greater than 15. So Q is going to, it needs to shift to the left to get this back down. 0.13 squared divided by 0.5 divided by 0.8 squared. This one is 0.05. So Q is much smaller than K. So it needs to shift to the right to increase the amount. At a certain temperature, okay, here's another ice problem. At this temperature, we have this moles and this moles placed into 1 liter container. What concentration of HI would be present at equilibrium? So this is an ice table. How do we know it's an ice table? Because they tell us this is placed into a container. So initially, this is this. So we're saying how much of this is, how much do we have at equilibrium? To HI. Let's say 0.7, 0.70. I'm setting this up, and K is 53.3. And this may look like a really doozy of a problem. And if you do not see what I am going to show you, this would be a really doozy of a problem. But however, this is a actually ingenious problem because of how it's set up. So this is going to be minus x. This is going to be minus x. This is going to be plus 2x. This is going to be so 0.7 minus x. This is 0.7 minus x. This is going to be 2x. So we have our K. K is equal to HI squared over H2 times I2. So this is quite a doozy. Plug these values in. What do you get? 2x squared or 0.7 minus x times 0.7 minus x, which is the same as 0.7 minus x squared. Now, before you evaluate and make your life hell, what factor are they both up by? They're both up by a factor of squared. So what could I do to both sides of the equation to simplify this? Square root both sides. I'm going to move this over here to avoid. So the square root of 53.3 is 7.301. And the square root of 2x squared is 2x. The square root of 0.7 minus x is 0.7 minus x squared is 0.7 minus x. So now this is a lot easier. I still have to get the x's by themselves, but I no longer need a quadratic. So I get these x to the other side. So we have 7.301. We'll just say 7.30 times 0.7 minus x equals 2x. Now evaluate. 0.7 times 7.3 is 5.11 minus 7.3x equals 2x. Now here's our pre-calculus. We add that to the other side. You get 5.11 equals 9.30x. 9.30. So 5.11 equals 9.30x. So to get x, 0.30, 511 divided by 9.30. So our x is 0.05, we'll say 549. Now, however, before we answer this, what do they want to know? They want to know the concentration of HI. The concentration of HI. So we got to remember, before we finally answer this, what was the concentration of HI? Concentration was HI was not X, but 2X. So for those who aren't here, who don't watch this, will probably get this one wrong. Maybe a couple times. But so we don't just want that value. We want that value times 2. Times 2 gives us 0.1098, which we can round up to 110 molar equals HI, which is 2x. One zero. What? Okay, let's figure this out. Square. What? Oh, 53. Let's see. Square root of 53.3. 3.7 x. Okay. 5.3 divided by 9.3. Okay. Sorry. Here's my problem. Here's my one problem. Sorry for the. My problem was here. When I did that 5.3 divided by 9.3, it should have read 0.549. I had an extra 0. So this number becomes 1.10. Off by a factor of 10. However, I got that. So the correct answer should be, unfortunately, it doesn't know how I screwed that up. So that's all the time we have for today. We're absolutely out of time, but the last questions we have, like another ice question, but hopefully somewhat easy. And we have some Le Chatelier's Q equals K kind of situation here. Le Chatelier's the Chateliers, the Chateliers. So hopefully that is a good start for you guys. Hopefully we can get through this. I want to thank you for your time, and I will see you guys either in lab tomorrow, or I'll try to send an email before lab once we know what's going on. But I'll see you on class on Thursday, whether virtual or whatnot, what have you.